Okay, so this is, I think at least some of you attended the SEM webinar almost exactly a year ago, November last year. So in that seminar, I talked about power electronics in power systems. And so what I do today is because that's kind of the basics for a lot of the work we do. So what I do is today just go back to that quickly. Just go through this some highlights of the slides. That's the first section here, power electronic power system, what I presented to the group in November 2020. And then talk about small signal sequence impedance theory, the basic ideas behind the small signal analysis method we developed. And then go into the converter modeling, just a few slides to talk about why that's important. And then a couple of applications. One is something we've been working on for more than 10 years, and that has to do mostly with stability at the interface of the converter and the grid. So it's more like individual converters, wind farms. And so that's been like a focus for our work for some years. But in recent years, because of the increased use of power electronics, we really started to talk about the so-called converter-based power systems. It's not just individual converters or wind farm integration, but really a different power system. So that's the last point I want to just give a brief sort of introduction to the latest development in that direction. How do we expand the small signal methods to study that kind of power system? So the next few slides are kind of a summary or taken from the last year's presentation. So this is a busier picture, but the idea is to show how power electronics is penetrating the grid. So, for anyone who knows the power system, we divide the system into generation, transmission, distribution, consumption. The pictures kind of makes it clear that we have converters and increasing use of converters in almost every sector of these system. Right, from electrical vehicles on the loader side, electronics, data centers, microgrids at the distribution level, to high voltage DC transmission, renewable generation from wind and PV, and then maybe difficult to classify like the energy storage. That could be installed at distribution level, transmission level. It's not generation, but it's supporting the system. So I think this is the international movement. Certainly we saw that everywhere in the world. And power electronics obviously enables this transformation. So when we talk about 100% renewables in the future, a lot of I think last year I showed some maps, this so-called carbon neutral economy, decarbonized power system. That's really becoming a policy framework in many countries. That the desire to move to a carbon neutral economy, right? And so but to do that, we really have to get to 100% renewables. And if we look at 100% renewable generation, you can argue the power system would be more than 100% converter based, because often the power has to be processed twice for many applications. From wind turbines, type 4 turbines, for example, you have a rectifier and inverter. So every megawatts turbine would require 2 megawatts of power electronics. So by that, in a percentage, you can argue 100% renewable power grid in the future really means more than 100% converter-based power system. And that's really an interesting transformation if you think about the 100-year grid. And now it becomes really different. So what does that all mean to electrical engineers? Obviously we have to make these converters. We have to worry about balancing the power and so on and so forth. But one of the key features identified last time. So this is again review from last presentation. If we want to understand the difference between traditional power system and future converter-based system, it really comes down to the difference between electrical machines and converters, because that's what we're replacing. And one of the difference identified is the different speed of control. So this was part of what I explained last year. Control of conventional generators is order of magnitude below the fundamental in terms of the control bandwidth, and for power electronics is the other side, the other way. It's like order of magnitude faster than fundamental. So you put these two together, the speed of control is almost 2 orders of magnitude different between machine and converters, and that has a lot of implication at the system level as well. So those who study power system probably recognize this diagram that defines different kinds of power system stability. Roughly speaking, we talk about rotor angle stability, frequency stability, voltage stability. If you measure these stability phenomena by time constant or frequency range, they all congregate at the lower left end. And that's because control of generators are slow. Right? So these are the typical control functions, maybe up to a few hertz for voltage control. Subsynchronous resonance, subsynchronous oscillation is another particular issue. But above, a few hertz, 10 hertz, we really don't have control in the traditional power grid. And because we don't have control in this frequency range, right, we don't worry about stability. Right. So this is what typically people refer to as electromagnetic transient frequency range. And because there's no stability, we don't have to study the stability. We run EMP simulation for some other purposes, but there's really no stability to talk about. So the traditional power system stability theory covers these, and can be done with fundamental frequency models, and everything's kind of perfect, right, for many decades already. Now with converters, we are adding a lot of more control functions with converters, and the really most important difference is that we are having these high frequency control functions. They are mostly related to the inner control, like current control, and then even the outer control loops of converters are faster than synchronous machines. And with this fast control, we introduce a potential for instability in the higher frequency range, where we didn't have the problem in the past, but now this is very common due to fast control of converters. I just want to emphasize that the converters do not necessarily cause problem in this frequency range. I think that often is a misconception. Fast control will lead to instability. Not necessarily, depending on how you design it. Certainly, it creates a potential, right? Anytime you have feedback, you have the potential for instability. And this is sort of the new challenge in terms of system stability, right? And obviously, when you have that stability problem, you need to study that. And the starting point for any stability analysis is proper models. And this, I think, is also one of the slides I presented. So you think about how to study stability in that higher frequency range, because the phenomena we are concerned about there are in the EMP, simply put in the EMP frequency range. So we need to start with EMP models, electromagnetic transient models. And people do a lot of simulation these days, a lot of dedicated software tools to do that. But we know simulation alone is not sufficient for designing the system. In addition to simulation, we need to have analytical means. We need to have a small signal analysis method that allow us to understand what is going on and be able to design the system. So to do that, we need to work with small signal EMP models. Why small signal? Because every converter model, you look at the time domain model, every converter model is nonlinear, right? So in order to perform frequency domain analysis, we have to linearize it. So in other words, we need small signal EMP models. And that's where the fundamental challenge, or one of the fundamental challenges, kicks in, because when you try to linearize an EMP model, when you apply the traditional method, you end up with a linear type time periodic model. And that model cannot be directly converted into the frequency domain to support more the standard frequency domain analysis technique. And this is obvious if you just think about a bilinear function between x and y. If you try to linearize it by introduce a small perturbation delta x and delta y on top of the fundamental, then you end up with these terms which represent the steady state, and then two small signal terms, each is proportional to the perturbation. So it's linear in this perturbation, but the coefficiency changes at the fundamental frequency. Right? So this is a time periodic model. And practically, we just don't know how to handle that. There's a lot of interesting research going on, but I would argue that nothing is practical for real system application. So this represents an important challenge. In order to address these a new stability problem in the high frequency, we need new models, but the standard linearization method doesn't give us that kind of model. That's sort of a quick capture of what I talked about last time. And then next couple of pages were also covered, but I want to maybe go through them at slower pace. So moving to the modeling aspect, how do we resolve that? How do we tackle that challenge? So the method we develop is not to linearize the nonlinear function directly as we used to do, but rather we do that in a frequency domain. So the method is what we call harmonic linearization. It's sort of based on the principle of harmonic balance. This table summarizes different ways to introduce the perturbation when you work with sinusoidal or fundamental voltage current. So the first two lines shows the amplitude of phase modulation. This is what you would do when you work with fundamental frequency models, right? Because your model is formulated in terms of the amplitude and phase angle of voltages and currents. So when you linearize that model, you effectively introducing perturbation to the magnitude of phase angle. That's been what people do for many years, right? But this model is not suitable for high frequency because we're looking at within what the dynamics within every fundamental cycle. So that cannot be captured by amplitude and phase modulation. If we directly superimpose the perturbation over time or as arbitrary function of time, this is where we run into this linear time periodic model challenge problem, right? So the method we apply is to introduce a perturbation in a sinusoidal form at a different frequency. So now your operation has the fundamental as well as a perturbation. Graphically, kind of can see from this diagram, right? So this shows the perturbation is at frequency higher than the fundamental, but that's not necessary. This just makes the graph easier to read. The perturbation omega p can also be lower than the fundamental. I just superimpose another harmonic on top of the fundamental. The magnitude should be small. The VP or delta VP should be small because that's the requirement for a small signal. You apply that voltage to the circuit or system you try to model, and that circuit, the converter will respond to this voltage with current at different frequencies, including the fundamental, including the response at the perturbation frequency, and then because of nonlinearity, other harmonic would also be present. Now for small signal analysis, what we are interested in is mostly the response at the same perturbation frequency. Right? This is a linear relationship we try to capture. And that component can be extracted by Fourier analysis. And then once you have that component, the ratio of that current response to the superimposed voltage response will define the admittance at that frequency. So this is the basic idea. And we can apply this principle to develop analytical models. So I just do all the calculation analytically, manipulate the equations, then you end up with a transfer function that describes these admittance. Later on, you will see there are more complexities in these, but in principle, this is how things can be done. We can also run simulations. So we have a detailed simulation model. We can introduce a perturbation like that, run the simulation into periodic steady state, and then do similar analysis numerically to extract the frequency response. And you build the frequency response point by point. So that's what we call frequency scan. You can scan the response over frequency. And we can do that by measurement or numerical simulation. We can set up the converter in the lab. We have an amplifier where we can use to inject voltage perturbation, and you can actually measure the impedance. So we have been doing that for many years in the lab. For small converters, a few tens of kilowatts, we can use an amplifier, audio amplifier, to inject enough perturbation, and then you can measure these kind of response. So the same principle can be used to derive the frequency response or admittance model in analytical form, numerical form, by simulation or measurement. Right? So that also allows us to directly validate any models we develop. And later you'll see this is a major advantage of the method. So that's one side of the theory, the ability to develop frequency domain response or models to represent each converter, no matter what type of converter it is. Now, the next part of that, the theory we worked on, is to use that kind of small signal frequency domain model impedance at the system level to study stability of the system beyond just the converter. And the assumption we make is that the converter is stable if you connect that to an ideal grid, an ideal voltage source. So the concern is when you're operating with the actual grid, whether the system can be stable. So to study that, we can represent the system by a grid with one converter. So this is a simplified representation. The grid can be modeled as ideal voltage source behind the impedance. And the converter, particularly the so-called what we call now grid following converter, can be modeled by a current source in parallel with admittance. So this simple equivalent circuit describe the small signal behavior of these converter connected to the grid for the phenomena that we are interested in the high frequency range. If you inject a perturbation into this interconnection point, you can model the response of that voltage. Right? It's a simple mathematics. And once you have that transfer function, you will immediately see that that is actually equivalent to a feedback loop where the grid impedance is a forward gain and the converter admittance is a feedback gain. And these two form a negative feedback loop. And the transfer function of the equivalent circuit or the converter grid system is equivalent to the transfer function of this closed loop system. So that makes an interesting association between an electrical system of converter and grid with a simple feedback loop. And what that means is stability of the converter connected to the grid is equivalent in small signal sense, equivalent to the stability of a single input, single output feedback loop in this form. And that's the kind of idea I presented almost exactly 10 years ago in this short article letter. Now, everyone knows how to determine the stability of this feedback loop, right? We just apply the Nyquist criteria. So that makes system stability analysis possible with the kind of small signal frequency domain models at the converter level. Now, there's also another interesting aspect here, which is practically, we look at practical applications. Both of these transfer functions, ZG and YC, are guaranteed to be stable. Why? I mentioned for practical purpose, the converters should be stable when it's connected to an ideal voltage source. Because no matter who make the wind turbine PV inverter, if they can sell the product, obviously that converter has to be able to operate stably, at least when it connects to an ideal grid, right? Nothing else. That's a minimum requirement, otherwise you cannot sell your product. And on the other side, the grid, before the converter is connected, without the converter, the grid should be stable, because otherwise there's no point of connecting a wind turbine to it. So these practical considerations can guarantee the stability of the open loop gain ZG and YS. Okay. Now, once that guarantee, then application of the Nyquist criteria does not have to check the right-half plane zero of the open loop gain, because there should not be any right-half plane zero in the open loop gain, but it's guaranteed to be stable. So this is an advantage, but this advantage becomes more apparent when we extend these to multiple converter systems. And this is the reason we formulate this feedback model, because you can argue that the stability can be determined based on this model, mathematical model, or original model. It's not difficult to calculate the pause of this transfer function. And once you check there's no right-half plane pause, then you know this system is stable, right? So it's not necessary to work with the feedback loop like that. But the feedback loop, because of practical considerations, simplify the problem and give us a lot of more insight. And that's the reason for using this kind of feedback model. So that's the basic idea. Now, when we apply these to three-phase power system, obviously anything we talk about in the grid is three-phase, right? So to extend all these mass modeling and system analysis method to three-phase, we need to expand also the concept of the impedance. So to model three-phase converter, for example, right? Because there are three phases, so we're supposed to apply small signal perturbation to each phase. Right, so three-phase voltages, the three-phase perturbation should be at the same frequency. That's the principle of small signal analysis. But the amplitude and phase angle among the three phases should be independent. We don't want to confine this perturbation to a particular direction, because that will limit the exposure of the dynamics. So you may end up with a special model instead of a general model. So mathematically speaking, we want the three-phase perturbation to be independent, to be arbitrarily with respect to each other. But if you impose that kind of condition, mathematically it's impossible to work with, right? So what does it mean to be arbitrarily, right? So there's a mathematical difficulty, and to get around of that, we basically combine these small signal method with symmetrical component analysis. So the idea is an arbitrarily set of three-phase voltage or current or anything can be decomposed into balanced three-phase in a positive sequence, negative sequence, and zero sequence. In each sequence, the three phases are balanced, right? So the same magnitude, and the phase is displayed by 120 degrees. So that's a symmetrical component analysis. In traditional power system theory, we apply these only at the fundamental frequency, but there's nothing stopping us from doing the same thing at any frequency. So we can apply these to the fundamental as well as the perturbation frequency omega p. Now this also tells us that if we want to apply a set of three-phase perturbation, arbitrary perturbation, right, we can apply a set of positive sequence perturbation, a set of negative sequence perturbation, and a set of zero sequence perturbation. Instead of directly three-phase, we can just apply these balanced three-phase perturbations. And because we are interested in small signal analysis, so in the small signal sense, whether you apply the positive and negative sequence perturbation at the same time or separately and determine the response one at a time and superimpose the response on top of each other, it doesn't really matter because we are interested in small signal response. So instead of applying a combination of positive, negative, and zero sequence, we just apply a perturbation in one sequence at a time and define the response, and then change the sequence and repeat it because the response in small signal sense is additive. So that's kind of where the sequence impedance come in, because you apply a perturbation in the positive sequence, you are exposing the positive sequence response of the converter, and that's what we call positive sequence impedance. Right, so we do that in positive sequence and negative sequence. We normally don't do zero sequence perturbation because a three-phase converter without neutral cannot have a zero sequence current. Right? So the zero sequence is effectively open circuit with infinite impedance, so you don't really have to model it. EMI is certainly a different issue, but EMI is separate from stability consideration. So this is where the term sequence impedance come in combination with the small signal method we call sequence impedance, small signal sequence impedance, or small signal sequence admittance, depending on the form of the model. And based on that, the system model we developed would also have two parts. If we ignore the zero sequence, we would have a positive sequence model, which is same form for a single converter connect to the grid. You got a positive sequence, a source model, positive sequence converter model, and then a negative sequence. So the three-phase system is effectively decomposed into a positive sequence subsystem and a negative sequence subsystem. And the stability of the three-phase system is equivalent to the stability of both positive and negative sequence subsystems. So you have to have both sequence subsystems stable in order to guarantee the three-phase stability, right? If you have instability in the negative sequence, you're going to observe that in actual operation, also in the negative sequence. So this is how we apply the method to three-phase converters and systems. Now, the mathematical model assumes just one converter, but that doesn't really limit the application to one converter, because multiple converters at the same location, if they are close enough, integrate to the grid at the same point of common coupling, can be treated as one equivalent converter. You can do that by aggregation, so just calculate the equivalent impedance of the multiple converters connected together. You can have some line impedance in between, but as long as they're close enough, you can aggregate them into a single impedance. You can also reverse the model, and instead of aggregating turbine converter impedance, we can scale up the grid impedance to represent the equivalent source for one converter. So if I have 10 converters, for example, if we ignore the impedance between converters, then I can divide the impedance of one converter by 10 to represent 10 converters if they are more or less the same. If they're not the same, then I just need to connect the impedance in parallel. Right, so that's aggregation. Or I can just use one converter and then multiply the source impedance by the number of converters, and that's scaling. Scaling is limited to the case where you have identical converters. Otherwise, the aggregation would be more convenient to do. So with this simple model, we can actually study many different systems, including larger wind farms and PV farms connect to the grid. HVDC transmission certainly involves one converter at one end, so that's easy to model by this method. Right, so that's the theory. Now to support that, we need to build converter models for different applications. The principle, I explained that before, is just a fundamental principle. In reality, we need to build models for different type converters, and by converter we really mean also converter-based devices like wind turbine, right? Where you not only have converters, you also have the machines, type 3 turbines, type 4 turbines. So converter here is a generic term. It represents devices that are based on converters. So I want to go through this part over the next few minutes. Why do we need to have these converter models? The basic principle that I explained before can be applied in analytical form, can be used to measure the frequency response, or can also be obtained the frequency response through simulation. So you can obtain the necessary frequency response in different forms. And practically, simulation is a very common method now, because with big turbines, it's hard to measure the impedance in the lab. But you can build a very detailed model and then use numerical simulation to scan the frequency response. So that's kind of very common practice. However, I want to emphasize that nothing can replace analytical models. For system stability analysis. At the end, we need frequency response. But before that, there are many things we can do, and the analytical models allow us. So proper models are essential for the application, obviously. And some of you may have heard about other modeling methods. For example, the DQ transformation. I didn't explain that before, but one way to overcome, or another method to overcome this time periodic operation of grid connect converter is to transform the model into a DQ reference frame, right? So if the DQ transformation is synchronized with the terminal voltage, then the balance three phase becomes DC, and then you can linearize the model. So you basically have a DQ frame model, and you can treat that as impedance. However, that model is not stationary. It's rotating at the synchronous frequency and locked to the voltage at the terminal of each converters. So if you have only one converter, that's fine, because there's only a one DQ reference frame. If you have multiple converters, many converters, every converter would be in its own reference frame, but then you have to piece them together to study the whole system. So that becomes a very challenging issue. The sequence impedance model, the small signal sequence impedance model we developed is in a stationary frame. There's no rotation involved. So naturally everything fits together no matter how complex the system is. So that's a major advantage. I mentioned frequency response can be measured, can be numerically simulated, but the ability to develop analytical models is important. Let me just show you how we do that in general, and then give you some examples. When we apply this general principle, harmonic linearization, to different converters, there needs to further expand the method. And this is because of the different types of converters we have to model. So for two-level voltage source converters, and the application we have for them, like most wind turbines, PV inverters, right? The steady state operation can be assumed to be harmonic free. In principle, they shouldn't be harmonic, right? So the perturbation will be added on top of the fundamental, and that's what we call single harmonic linearization. We are linearizing along the trajectory of a single sine wave, which is a fundamental, but in general term, we call it harmonic. Right? And that's the bulk of the converters and models we develop. But when you try to model modular multi-level converters, for example, the second harmonic cannot be ignored. Right? The second harmonic in the arm capacitor voltage is inherent, and that can also lead to second harmonic circulating current. And to suppress the second harmonic circulating current, you have to introduce a second harmonic control signal. So on top of the fundamental, you also have second harmonic in a number of variables. So to capture all that dynamics, right, we need to include the second harmonic as part of the operation trajectory, so to speak, right? The steady state operating trajectory needs to include the second harmonic. And so the linearization becomes a multi-harmonic linearization because the trajectory is defined by more than one sine wave, and that's multi-harmonic linearization, specifically for modular multi-level converters, but we also use that in two-level converters to account for the DC component of the DC bus voltage, for example. The last one is the further generalization of the so-called infinite harmonic linearization. And this is unique to line commutated converters. If you imagine an ideal line commutated converter, 12 poles or 6 poles converter, right? If you ignore the commutation, ignore the ripple, then the phase current is a square wave. So that's essentially the steady state. And if you look at in frequency domain, that square wave has infinite number of harmonics. Right? So to account for that, we need to consider the square wave type of trajectory instead of just a few harmonics. And the corresponding method is called infinite harmonic linear. So we have these kind of further development to suit the needs of different types of converters and be able to develop the analytical model. And that's kind of a bulk part of our work, and several PhD dissertations were written. So typically modeling one converter is a PhD dissertation. Build through the mathematics, validate and demonstrate application. Because of lack of time, I'm going to skip this next page. This shows how we, apply multi-harmonic linearization in analytical form and develop the model. At the end, it's still the transfer function model that we look for, but the intermediate steps involve multiple harmonics, and it can be quite elaborated mathematically. But we have done that for a number of converters. I want to give you a flavor of why we really want to have these analytical models. So these equations, they look complicated, but if you know how to read them, they really make sense. So what we have here are the impedance models for different types of wind turbines. If you know wind turbine, we call type 1, type 2, type 3. And type 4 turbines. Type 1 is really just induction machine, induction generator. So this is induction machine impedance, but at variable frequency. And then type 2 has the slip ring with a resistor connect to the rotor winding to regulate the speed. So that has extended term. This represents the externally connected resistance. But there's no converter, so it's relatively easy to model. Type 4 turbine, on the other hand, is just a converter connected to the grid, right? Get a rectifier, get a DC bus, and get the inverter. And the impedance is dominated by the inverter. So this equation shows the positive impedance of type 4 turbine, or in other words, the inverter. It's complicated, but if I explain to you, you will see immediately what it is. So you just ignore the denominator for a minute. The numerator, we have the impedance of the field inductor, the converter, what we call the boost inductor, right? So that certainly is part of the impedance. So that's the hardware, and it makes sense. It's the inductor impedance. The second term here represents or correspond to the current compensator. So what this equation tells you is current control of converter is equivalent to adding a series impedance, right? So your proportional gain in the current controller is a resistor effectively, right? That provides damping. And the integral gain in this form appears as a capacitor in the impedance, okay? So without anything, you get inductor from the filter, you get a capacitor due to the integral gain of the current compensator, you get the damping due to the resistance, okay? So it's perfect ILC circuit. However, if you include the delay, for example, control delay, then at high frequency, that positive proportional gain will become negative because of phase rotation by the delay. So you end up with negative damping at high frequency, right? So many things can be explained based on this simple model. Just look at it, the numerator. The denominator is introduced by the phase lock loop. And so these terms represent the phase lock loop transfer function. And that couples the current compensator into the model, as well as the steady state operating condition. So now because of phase lock loop, the impedance also changes with the power level and power factor. However, this transfer function of the phase lock loop is only active in a narrow frequency range near the fundamental. That's the bandwidth of the phase lock loop. If you keep a reasonable bandwidth in the phase lock loop, these functions would only have appreciable gain near the fundamental frequency. If you move 10, 20 hertz away from the fundamental, then these gain virtually disappear. So you really just have the numerator, the impedance that I explained before, right? However, when you're close to the fundamental, these phase lock loop introduce additional complexity. And that's where you have to be really careful with your design. Particularly if you have potential resonance near the fundamental, then design of the phase lock loop becomes really important. At higher frequency, above that 10, 20 hertz away from the fundamental, it's really dominated by current control. Right? So you can make a lot out of this simple model. DFIG, or the type 3 turbine, has similar form of model. You read it. So there's some added complexity here, but that's really because of the more complex impedance of the induction machine. The induction machine has inductance, but also resistance, and the rotor winding resistance has to be converted through the air gap, so that introduce this slip function. But the form of the model resembles that type 4 turbine. So there's a lot of similarity and common features that we can understand. And that's really the value of analytical model. It's not just some frequency response that you plug into a formula and get plots. It gives enormous amount of insight. So that's the value analytical model. That's why we keep doing that. And the latest development in that direction is what I published recently in this 2-parts paper in the Open Journal of Power Electronics. So what I propose there is to treat a 3-phase converter as a 2-port network. And one port is on the 3-phase side. It's a 3-phase, but we represent by sequence. So effectively, you can use 1 phase to represent, but consider positive and negative sequence. The other port is a DC bus, right? So the 2 sides are at different frequencies, but by harmonic linearization, we can develop the different transfer admittance. So these 9 admittances provide the complete characterization of this converter. And 3 of these are redundant because of relationship between positive and negative sequence. So effectively, you need 6 transfer functions to fully characterize a converter as a 2-port network. And the advantage of this 2-port network model is that it allows us to use the model as a building block at the system level, because converters are kind of the building blocks at the power system level. So to model a power system, we also want the converter model to be used as a building block. And this 2-port network allow us to do that, and particularly when you have to consider DC and AC system together. Right? The converter couple them, and these transfer admittance allow us to model them together in one model. So we can use this model, we can study not just AC grid, but also hybrid AC and DC grid. DC system is certainly simpler, because if you only have DC, then the linearization is much more straightforward. So we don't really have any difficulty. And so that's kind of the latest development. We develop analytical models. Next, I want to go through some of the applications. So the first is stability of converter grid integration. So this is really looking at the stability of individual converters when they're connecting to the grid. So it's a simpler model, and the system model is represented by that single input, single output feedback loop, if you recall. Right, so you have the converter admittance and the grid impedance forming a feedback loop. And through aggregation, we can consider wind farms and PV farms. So that's kind of the system we are starting here for this part. I want to just give you some example to show how we perform that kind of analysis, right? But first of all, just some measurement to indicate and show what kind of problems we're talking about. So this is a kind of really old measurement, more than almost 15 years old when we first started. It's a PV inverter connect to the grid in the lab. And to emulate different grid, we purposely inserted an inductor between the inverter and the grid. So by changing that inductance value, effectively, we're increasing the impedance of the grid that the PV inverter sees. So it's a kind of way to emulate different grid conditions. So if we don't insert any inductor, the grid in the lab is pretty strong, the distribution circuit. The inverter has no problem operating with it. You can see that both voltage and current is some almost perfect sine wave. When we increase the inserted impedance, you start to see this harmonic distortion. Now, a lot of people look at these will say, this is harmonic distortion of the PV inverter. Well, it's not really this just the inverter, because without inserted impedance, the inverter doesn't show any of that harmonic, right? So this is not harmonic emission by the inverter. This is related to the inverter operation with the higher source impedance. It's getting, if you connect that with the feedback model, it indicates that the system, the feedback system, is becoming marginally stable. So periodic disturbance in the circuit excites this resonance, and that becomes a sort of sustained harmonic. It's not unstable yet, right? But it's indication of lack of stability margin. When we further increase the inserted impedance, the instability occurs. So the inverter cannot be connected stable. It just cuts off. And then because we didn't disconnect, so after cycle or two, the inverter will start over again. We cannot sustain a stable operation. So this is a good example to show, how the impedance, the strength of the grid can impact the stability of the grid connect converter. This what I'm showing on the right is an actual measurement in offshore system. It shows actually in reality how resonance occurs. So these are steady state pictures. I see the waveform being steady state, but this is more of a transient where a configuration in the operation triggers an underdamped or undamped resonance, and that creates a harmonic that increase over time. So the harmonic grow, you can see the harmonic increases, right? And the frequency of the harmonic is not a multiple of the fundamental. As you can see, the wave shape is changing, and the growing harmonic can also be seen more clearly on the top, right? So you can see that resonant harmonic keep growing, and eventually, this will either grow to a point where the system will shut down because of protection, or will cause damage to some components, right? Either way, or in some minor cases, this harmonic may grow to a certain level. If it's not significant enough to trigger protection, it doesn't continue to grow, that may sustain at a certain level and then continue for some time until the operating condition changes. And this is very common in practice. How do we analyze that? So based on the frequency domain models, like this is the frequency response of the two impedance. We plot out the source impedance, the grid impedance versus the turbine or converter impedance, magnitude response, phase response, and the Nyquist stability criteria, because we don't have to worry about right half plane 0 or pulse, right? We can just simply look at the Bode plots and look at where the magnitude intersects, like at those points. And at the intersection frequency, we can look at a phase difference. And the phase difference can tell us whether the system encircle -1 point, or whether the system has enough phase margin. So this is kind of a common technique we apply to analyze the operation of the system, right? Again, based on frequency response, look at the phase margin, the intersection frequency. If a system, the magnitude intersect at certain frequency, like here 20 hertz, right? And you look at the phase difference at that frequency is larger than 180 degrees, and this indicates unstable resonance. The magnitude, equal magnitude, indicates a series resonance, because you got one side, you got a capacitive impedance, right? The magnitude drops with frequency. On the other side, you got an inductive impedance. And when the magnitude become equal, that basically indicates a series resonance. And the larger than 180 degree phase difference indicates that the net damping at that frequency is negative, right? So it's unstable resonance. Based on that, you can predict unstable resonance in the system at that frequency. So this is kind of standard technique we apply to analyze the system once we have the model. This has to do with turbines, different turbines with overhead lines, but we also apply that to various systems. Type 3 turbines with HVDC converter, for example, in offshore environment. And this is characteristic of a type 3 turbine. The impedance is very inductive because it's dominated by the induction generator. However, the converter behind the generator creates a negative damping and causes the phase angle to go above 90 degrees, which is an indication of negative damping. And that intersects with the capacitive impedance of the HVDC converter in that frequency, right? So you form a perfect series resonance, and the phase difference will determine whether that resonance is stable or unstable, right? So frequency domain analysis supported by either time domain simulation or measurements in the lab. That's kind of how we perform the analysis, what we call case studies. MMC-based HVDC converter has some unique issues, and particularly in the high frequency because of control delays. High frequency resonance is very common with MMC-based HVDC converter. So this shows a startup of offshore wind farm where the HVDC converter starts first and energize the offshore cable network. The turbines are not connected yet. But during that time, the cable network impedance, because it's unterminated cable network, the impedance is capacitive from the cable. And that caused this series resonance with the HVDC converter in that 500 hertz range, 455 hertz range, where the MMC impedance is dominated by the arm inductor. So you're above the control bandwidth, any of the control bandwidth, you only have the arm inductor left. That gives you the inductive impedance. However, the control delay in the MMC adds a negative damping on top of the inductive impedance. So it's inductive impedance, but with phase angle larger than 90 degrees. So when you have a resonance with the cable network, that becomes unstable resonance, and this will lead to this growing harmonic at that 455 hertz that you can predict from this analysis. And what this means is that the offshore wind farm cannot start. You cannot energize. You cannot establish the offshore AC grid voltage. To solve that problem, we have to modify the control, for example, right, to avoid that resonance. Sometimes practically people find if you can energize the cable network in different sequence, right? Instead of, for example, connecting all strings at once, you may connect one or two strings first and then get a turbine energized. If you are lucky, you might be able to start the system, because if the impedance changes, you may move to a different frequency range where you have resonance, and then that resonance may be stable, but there's no guarantee. So the better solution is to damp the MMC impedance and allow the system to start under any condition. So once we understand this behavior, you know what to change. You go back to the converter design and couple that with the converter analytical model, we can find all kinds of solutions to the problem, right? So that's kind of the three P's of our study. Develop models, use the model to perform system level study, and then from that case study, we identify different solutions to problems. Now, we have to move beyond that, but this is kind of how we've been progressing. Again, you can have similar high frequency resonance on the onshore side, HVDC over overhead transmission line. Long transmission line also has these multiple resonance issue you may have to worry about. So there's a lot of commonality in the high frequency. So those are the kind of case studies. And before we wrap up this part, I want to just maybe share a little bit practical background. So we started this modeling work, a lot of that in 2007, 2008. By 2012-ish, we kind of have the framework. We did a lot of trade study. At that time, not many people knew about practical problems, so you hardly read about it, and those who have seen it wouldn't tell you, right? So when I give this kind of presentation, often in the audience, particularly power system people, could say, "Oh, nice theory, but we didn't have the problem." That completely changed around 2014. So I captured some pictures to show these number of applications I've been sort of personally involved. The first one is the German offshore wind system with HVDC transmission. They had a major incident in 2014. So I worked with TenneT as a consultant actually for about a year to solve, analyze it, so the standard procedure we worked on, right? Develop models, perform analysis, develop solutions. Right? So that's an interesting experience. It's offshore HVDC transmission with wind turbines. And just about time we wrap up that project, there was an interesting incident in the west part of China. That was on July 1st, 2015. In this area, circled area, some of you may know, this is the Harmonic area, Xinjiang province, Harmonic area. These lines shows high voltage DC transmission, but that area has like 10 gigawatts of wind with several gigawatts of synchronous generators, really complex system. They had a different type of resonance. So the offshore resonance in the German North Sea was in the few hundred hertz range. But this system has a resonance in the near the fundamental, right? So there are actually two harmonic near the fundamental, and different types of turbines, classical HVDC converters. So really complementary to the first project I worked on. I spent most of my sabbatical in Beijing working with the state grid on that issue. So it was a very interesting project. In the last couple of years, I've been working on the load center. So interestingly, when we build these large load center data centers with hundreds of megawatts of loads, stability of that distribution system also becomes a real challenge. So there was resonance issues in data center power system. We also wrote a couple of papers. So these are more or less all in public domain. So you can read about, but yeah, so that kind of incidents, representative incidents, larger scale, each kind of serve a wake-up call to the industry. And that triggers a lot of interest, and industry, I would say, in the last 5-6 years really changed in this area. Because when you have, before, people don't know about this, but when you have the problem, you start to model it, analyze it, and then you develop what I call ad hoc solutions. But once you learn enough about these, people start to ask you, how do we prevent these? We don't want to wait for the problem to happen, first of all, but we don't want to just keep doing analysis, right? So how do we prevent these problems and minimize the amount of analysis? So now we are really moving into the next stage where we talk about standards, the grid codes that will impose additional requirements on converters that in most cases can guarantee stability in certain frequency range. So that's kind of natural progression of the technology. It's really happening in some part of the industry, at least for the data center, for example. We develop impedance-based stability requirements for the power supply now, and that's being implemented. So that's a lot of the application up to recent years, and I think I would consider that to be more or less mature area in terms of modeling, analysis, and developing ad hoc solutions. What we are doing now is to turn all that knowledge and experience into sort of design guidelines, design requirements that can avoid most problems. And the new challenge now is a larger scale. So now instead of individual converters and wind farms connect to the grid, we really start to talk about converter-based power system. So this is a simple picture to show what we mean by converter-based power system. It really means many converters, not just one converter, right? In reality, the converters will be embedded in the grid, but just to make it easier to see, I purposely pull the converters out, put them on the outside. But you have multiple converters connect to the grid at different points. If you want to analyze this system with the impedance-based method, right, we can certainly replace every converter by the admittance impedance, so the whole system becomes a linear network. We can do that, right? But then to apply that single input, single output model, we would have to look at one converter at a time and lump the rest of the converters with the grid into the equivalent grid, and then we formulate that single input, single output model, and then we repeat that for every converter repeat that for possible combinations of converters. By doing that, we would get a pretty good idea about how all these converters will interact with the grid, right? However, this is really tedious, right? Really tedious. It has a lot of limitations because each time when we pick one converter, we have to model the rest of the converters with the grid. So we have to rebuild all the models. The result may also change with the sequence. While we look at this converter first, that converter after, or reverse the order, you may get different results, and particularly when the system is marginally stable. Right? We have additional connection between converters like HVDC. We really want to look at the two converters together instead of one converter at a time. Then you have a difficulty breaking this system. Right? So this is the inconvenience when we just try to apply the existing single input, single output model to the converter-based power system. So we clearly need to extend the theory. Just to give you indication about practical complexity, this is the system I showed you before, what I worked on 2015, 2016. This is the sort of simplified single line diagram showing the local AC network. Want to highlight a couple of things. So there is this HVDC converter on the lower left corner, 8 gigawatts. That's a classical HVDC, 800 kilo, plus minus 800 kV, transmission over 2,000 kilometers. Next, not far away from the HVDC station is this coal-fired power plant. So about 4 to 5 gigawatts. And the purpose for those are to stabilize the local AC network for that classical HVDC. So those who studied converters or HVDC, classical HVDC, knows that you need a decent AC grid, right, to operate a classical HVDC. And that's part of the reason of having those synchronous generators. The rest of the system is all wind and PV. So every dot you see in the map, those little dots, every one of that is a wind farm, and typically in the order of 40 to 50 megawatts. There's a lot of wind farms in this area. And the resonance happens in the whole system. You can observe that. So you try to apply the method I talked about before to this system, it's impossible, right? There's so many combinations. So the way we solved that problem was sort of iterative, assisted by measurement, because it's a real incident. You know the problem. We know the incident are related to harmonics. So maybe I can play this video just while I'm talking. You can see these harmonics symmetrical about the fundamental, and they wiggle around. That's unstable, moves up and down. Eventually shuts down. So we know there are these harmonics related to the incident in the area, and based on harmonic measurement of different lines, we were able to identify the most critical paths and simplify the system greatly to fit into that single input, single output model. And based on that, we were able to identify the root cause related to a certain type of wind turbine, and then by tuning the control, we solve the problem, right? But that's possible because we have the measurement. The incidents has happened and was still happening. So you can use measurement to reduce the amount of analysis, iterative, and be able to focus or narrow down. And you cannot do that when you are designing a system, right? So this clearly indicates that we need better theory to handle these complex systems. And that's what we are working on. Now, one more thing I want to add here is when we talk about one converter connect to the grid, the stability phenomenon is easier to define because we really worry about the ability of that one converter connect to the grid, right? It really doesn't relate to the stability of the power grid. It's a separate problem by itself. When we talk about converter-based power system at the system level, we have to make a better definition, because otherwise people can easily be confused with traditional power system stability. So this is a diagram taken from a recent report from the IEEE PES Society, and that defines the additional stability phenomenon besides the classical power system stability theory that you saw before. rotor angle stability, voltage stability, frequency stability. In addition to them, people added this block they call resonance stability, converter-driven stability. Personally, I don't like these terms, to be honest with you, right? But that's kind of what people are using. And so instead of using those terms, I will simply refer to them by frequency. So this is how all the kind of problems we're addressing. And they are different, again, from traditional power system stability by their frequency. And that's how I kind of refer to them instead of using the terminologies. So this is how we divide the frequency. High frequency, typically above the second harmonic, right? So in the US, it's 120 hertz. It's not absolute boundary, but above the second harmonic frequency, you have virtually all the inner loops already passed. So you just have little bit of the current control loop left and then some control delays. And that's what we call high frequency range. And below that and down to a few hertz is what we call the medium frequency. And this is probably more complex frequency range where you got many things coupling with each other. The lower frequency range is from below a few hertz is the low frequency. That's where traditional power system stability works in. So for us, really, our focus is medium and high frequency. That's where we focus on. That's where we need new models. That's where this impedance description gives the useful insight. So that's how we classify it. So I don't have the details yet. It's still a paper I'm writing, but we are extending this single input, single output formulation of a system model to this multi-converter system. So naturally, you come to a multiple input, multiple output model at the system level. But it's a linear model in the frequency domain. So once you develop the model, formulate the feedback form, then you have all sorts of linear control theory you can apply. Right? So that's bring us to the same level as a single converter. As the last page or second last page, I want to just give you a idea about where we're going to head to, because we are here to build up the future power grid, not to just analyze problems. So eventually, we have to find solutions. But to get there, we have to go through different stages. And this is how I define the different stages. The first stage is theoretical development, building the models, develop the theory. We are lucky, we should have the theory available before any incident happens, and that's kind of the case with the method we developed. So you have, once you have this theory, typically you have an accidental application like in the German North Sea, right? So you consider that accident. Not many people know about it, but if it's larger scale, then you kind of wake up call. People start to pay attention to it, you apply the method more broadly, but those are still isolated cases, and you have ad hoc solutions, so every system may be different. You develop the solutions, and those solutions are usually proprietary. People don't want to share. I still cannot share with you what I developed for those systems, right? That's a nature. But once you've done enough of it, you have the understanding, you have the experience. You say, oh, no, they are not really just isolated cases. There's some commonality, and therefore I can solve the problems with some common solutions. And I can also have standard procedures and tools to perform the analysis. Right? So that's a natural progression. And once you get to that point, the next step is, well, how can we fundamentally solve the problem instead of just keep doing analysis? That would be what I call stage 5. If I put these in together, look at high frequency and medium frequency, the two frequency ranges we are interested in most. Look at individual converter connect to the grid versus converter-based power system. I think we have made tremendous progress with individual converter connect to the grid. We're close to the stage 5 where we can have new standard grid codes and standard solutions. With converter-based systems, multiple converters, the high frequency range is simpler because the isolation among different converters by the impedance of the grid because the high frequency, the lines naturally sort of isolate the converters. The medium frequency is different. That's where you have a lot of coupling. Many converters now couple together, and they may also couple with generators. So we're really at the beginning where we just have this basic theory. We start to work with industry to apply to isolated systems. So hopefully in the next couple of years, we'll develop some knowledge and then be able to move up to stages 3 or 4. That's where we are in general. And I mentioned before, to guarantee stability, we want to turn a lot of these model analysis into design practice and standards. So we have been able to do that for data center power system. And this shows the consideration behind some of the specs. We actually wrote that in a couple of papers. If you're interested, I'll be happy to share with you. I run over time, but I want to leave this page here for you. This is really old papers. You look at it, it's from 1924 to 1954, before my lifetime and certainly before all of your lifetime. But the reason I put them here is you look at the development of existing traditional power system series, stability theory. It really started around 1920. Right? So the first paper I can find, theoretical considerations of power transmission system. That's the first time people talk about stability of power transmission system when you interconnect generators. So started in 1920, and about 20 years, most of that become mature. By 1940, at latest by 1950, it's done. The system, the series was established by then. Right? And after that, it's more like more computational tools, phasor mesh and so on and so forth. Right? That's some new development, but the fundamental theory was established over that 30-year period of time. But what's interesting today is we're kind of 100 years later, we're repeating it. But this time, it's not about generators. It's not about synchronous machines. It's converters, right? Right now, we're in 1920. And if you look at the policies that many countries talk about, by 2050, we have to be carbon neutral, right? So, this converter-based power systems here, it has to be done at least 10 years before that. So it's a very interesting coincidence, right? A century later, we're repeating it, and I think your generation has the opportunity to really get the job done. So with that, I'd like to maybe see if we have time for questions.